let's take a look at G-GMD.A.1, Activity 5. This activity focuses on building the formulas for the regular polygons. These guys are a step up in difficulty. You'll see why shortly. They involve special triangles and their ratios. And they are pretty essential to know, though, because if you're going to do volume of a hexagonal prism, a tetrahedron, a four-sided polyhedron, then you need to know how to do some of these kinds of things. And so we're going to look at these areas of the square, of the equilateral triangle, and the regular hexagon in particular. And we're going to look inside the shapes a little bit here and look at them differently, because you already know how to find the area of a square and of a triangle. These ones are kind of unique, so we'll look at them a little more up close. One of the things is a regular polygon can be inscribed in a circle. All of them can. And so one of the names that gets attributed to a measurement inside is called a radius. The radius is from the vertex to the center. And that's again because it is the distance out to the circle. If you think of the circle that's circumscribing these objects, that would be the radius. Another important measurement is the perpendicular to a side from the center. That's known as the apothem. And so it is placed here, called the apothem. Let me spell that for you. Now, that is a word that's been greatly debated over the years, and maybe you're getting a little bit of my West Coast, and maybe you're getting a little bit of my Canadian when I say apothem. It's said different ways in different places, so you might be laughing out there right now. You can see three little triangles are formed. These three little triangles are quite important in the calculation of these areas. Now again, with these first two, you can certainly do them in the techniques that you've used before. But these are an additional way, or additional types of information to find area. This guy in particular forms a very special triangle in here, and that is the 45 right triangle. And we already know a lot about that. That's why we studied that previously, is that in this case, this type of triangle has some characteristics: two equal sides of whatever measurement, and then the hypotenuse is exactly √2 times bigger than whatever those values were. So if these are 10 and 10, this is 10 √2, and so on. That does not always mean that the hypotenuse has √2 on it. These could be other types of numbers, and we would obtain something different here. But what we do know is that you're always to multiply or divide by √2 to determine the lengths of the sides between the hypotenuse and the legs. Over here, the triangle formed inside is a 30, 60, 90. The 30 being here, the 60 up here. And again, you and I have learned about a 30, 60, 90 triangle, and we know some things about what's going on there. So again, well, let me come back here. So let's talk about our few things here. This is the apothem, right? So the apothem is the same as half of a side. That's something to know. The radius is going to be √2 times bigger than the apothem, and so on. Here, again, you know that this is 2, 1, and √3 are the ratios comparatively to each other. So if this is 10, this is 5, and this is 5 √3. Again, you might want to go back and review the special right triangles. But also understand that this is the apothem here, and this is the radius. And so in this case, 2 times the apothem will equal the radius, because remember, if this is the short leg, double that will be the hypotenuse, which in this case is a radius. I'm trying to teach you how in these three shapes, there are these special triangles hiding there, and all of the numbers are determined based off of the special right triangles. Let's look at the last one. This is also a 30, 60, 90 triangle, but it's in its upright position. So when it's drawn like this, the 60 is in this corner, 30 and 90. And so it is the same relationship, but it looks like this. The apothem is here, the radius is over here, and this is half of the side length. See how it's half of the side length here. And again, the relationship between these measurements is double or half. Between these two is times root 3 or divide by root 3, and that becomes important. We'll look at a couple up close to help you. Part of the question you might have is, how did I know the angles here? One of the things that you know in a regular polygon is that the central angle, which is, let me show you the central angle. If you were to draw the radii out to the vertices, you know that the central angle is 360 divided by the number of sides. So this would be 120, 120, 120. In this case, it would be 90, 90, and 90, and so on. In this case, it would be a total of 360 divided by 6, which is 60. Now, where did I get the 30, the 60, and the 45? Is when you drop down the apothem, that becomes 45. When you drop down the apothem, that becomes 60. When you drop down the apothem, that becomes 30. And that's where those special right triangles are formed. And truthfully, that's one of the big reasons we spent time back studying those. Let's look at a few up close. I just want to quickly go through these three shapes one more time, a little more visually. So I had mentioned, first of all, that the regular polygons can be inscribed in the circle. So here's the equilateral triangle. I mentioned the central angles are all 120 in this case, because 360 divided by 120. But if you drop the apothem here, you get a 30, 60, 90 triangle, which is a very important thing. And all of the calculations are based off of that 30, 60, 90. But I also want you to catch a shortcut on a formula for these guys. It's a very simple one. It's only 1/2 the apothem times the perimeter. Now, where does that come from? Well, the idea is, think of three congruent triangles: base times height divided by 2, base times height divided by 2, and base times height divided by 2. The base in each of those cases is one of the sides, and the height in each of those cases is the apothem. And in these cases, all of the sides are the same, and the apothem will all be the same for this type of shape. So by doing a little bit of factoring, if I pull out the 1/2 and the a, I'm left with s, s, and s, which is the perimeter of the shape, s, s, and an s. So if you just take 1/2 the apothem times that perimeter, you get the value. And also, for some students that don't see this, I guess all I would say to you is you can just do the three areas. And so a lot of students just find the area of this gray triangle and then multiply that value by 3 to get the full one. This is true about the square as well. There are 4 little squares. You can see them in their colors here. And if I just did one of them times 4, that would get it. Another way to do it, again, is they each have a side and an apothem, and they're each 1/2 because they're triangles. And you see that formula again, 1/2 the apothem times the perimeter will obtain the full region. That also works just fine here too. There are 6 of these triangles, and so one way to do it is 1/2 the apothem times the perimeter. Basically calculates 1, 2, 3, 4, 5, 6 of them all put together. So this is a nice way to do it. And I guess I would remind you that the whole premise of the trickiness of this is that knowing what this shape is here, because this is how you're going to use your radius, your apothem, to obtain your side lengths and work overall. Same thing here, your apothem, half your side length, and your radius is found here. And finally, your apothem, half your side length. And again, your radius is here. This should help you get a pretty good head start on it. We'll look at some specific examples later. Let's look at a couple examples of how this works. And so we'll start with an equilateral. It says it has sides of 18, which makes this a 9 here and a 9 here. Now, this is a 30, 60, 90 triangle, and we know the relationship between the long side to the short side is either times root 3 or divide by root 3. So in this case, it's divide by root 3. So I'm going to quickly figure out what that number is. I get 9 root 3 over 3, and so I get 3 root 3. So this apothem is 3 root 3. We're all ready to go now in terms of calculating this. It's 1/2 the apothem times the perimeter. So 1/2 the apothem is 3 root 3, and our perimeter happens to be 18 times 3. And we're just going to multiply all that together to obtain the total area. Again, where does this idea of 1/2 the apothem times the perimeter is that there are 3 of these triangles that exist in here, and by calculating this one is basically 1/2 the apothem times the one side, but we want to do it by all 3 sides. So the calculation of this comes out to be 12 root 3. Units, I guess centimeters squared in terms of that. So the only tricky thing, I think, is this little business of going from this side on a 30, 60, 90 down to the apothem, which is a divide by root 3. Let's take a look at another example. All right, let's take a look at the square. It gives us a radius of 4 root 2. Now remember, this is a 45-45 right triangle. And so we would divide by root 2, which gives us our apothem, gives us this. Now, I am going to tell you a couple of things about finding the area of a square. Once you get one side, which seems to be 8, 8 times 8 is 64. So this is what I would do at this stage. But just to show you that 1/2 the apothem times the perimeter, now that would be 8 times 4 for 32. And then we take half of that times 4 is also 64 centimeters units. So, I mean, you know, the formula of 1/2 the apothem times the perimeter works just fine there as well. But certainly when you find the side is 8, 8 times 8 is 36. 64, sorry. Let's look at the next one. All right, this time we get an apothem of 7 root 3 in a hexagon. That's the long side of the 30, 60, 90 triangle. So we would divide by root 3, which gives us a nice number like 7. So actually we're ready to go at this stage. The area equals 1/2 the apothem times the perimeter. The apothem was given to us at 7 root 3, and the perimeter would be 14 times 6. And so if I quickly put that in the old calculator there, I get 294 root 3 centimeters squared as my area. And again, the idea is we're finding, you know, 6 of these triangles, and that's why we use the perimeter, because it's doing the 14 along each of those, and it finds the total area for us. Good luck with these.